Track 5, Airplane Systems. The examiner confirmed Robin's ability to determine the airplane's flight parameters for today's conditions. Now he's going to test Robin's operational understanding of the mechanics involved with flying an airplane.
Robin, let's talk about what's involved in flying an airplane. Tell me how you're going to use the flaps.
Well, flaps are movable panels on the inboard trailing edge of the wings. They are hinged and can be extended downward into the flow of air beneath the wings to increase both lift and drag. What they do is allow a slower airspeed and a steeper angle of descent during a landing approach. I can also use them to shorten the takeoff distance, so I'll use them on landing and to demonstrate a short field takeoff.
What hydraulic systems are on this airplane?
Hydraulic-wise, we have the braking system, the nose strut, and the nose wheel shimmy damper.
How do you steer this airplane when you're on the ground?
This airplane has a nose wheel steering capability. It's basically a simple mechanical linkage with the rudders. When I press down on a rudder pedal, a spring-loaded bungee or push-pull rod connected to the pivotal portion of the nose wheel strut turns the nose wheel.
And what type of engine do we have in this airplane?
The Cessna 152 is equipped with a horizontally opposed four-cylinder overhead valve air-cooled carbureted engine. It has 110 horsepower and is made by Lycoming.
And speaking of carbureted, what does a carburetor do?
A carburetor basically mixes fuel and air in the right proportions to form a combustible mixture. It vaporizes fuel into small particles and then mixes it with air. It also measures the airflow and meters the fuel.
So what's the significance of icing when it occurs in a carburetor?
The significance is it can make my engine run rough or even quit. I need to be alert for it when the temperature is between -5 and 20 degrees Celsius, which is about 70 degrees Fahrenheit, with high humidity or visible moisture, or when the dew point and temperature are close together, and particularly when I have the throttle low or closed. Anytime I have the power below the green arc, I want carb heat on. I do this by operating the carburetor heat valve, which directs unfiltered heated air into the induction air manifold before it gets to the carburetor. I'll watch the RPM. There should be a slight drop, then a rise again once the ice is all gone, and then the engine should run smoother.
What would you do about a partial power loss in flight?
Whether it's a partial power loss or a complete power loss, I'd set up a glide at my best glide speed of 65 knots and find a good spot to land. Then flying toward that area, I'd try to restart the engine by applying carb heat, cycling the fuel selector, bringing the mixture to rich, cycling the mags, and checking that the primer was in and locked.
What about an engine fire? What would you do if that developed in flight?
Right away, I'd want to eliminate any source of combustion. I would pull the mixture to idle cutoff, switch the fuel selector off, and turn off the mags. Then I'd pitch down to at least 100 knots, attempting to blow out the fire and find a good field to put the plane down in.
I really don't think either of these things are going to happen today, but it's always good just to have a plan, just in case. Now, what do throttle and mixture controls do?
The throttle controls the amount of fuel or air charge entering the cylinders, which regulates the engine's speed and power. The mixture controls whether the fuel-to-air ratio is too rich or too lean. This lets me adjust the mixture at high altitude as the air density is decreasing. I can also lean the mixture during cross-country flights to conserve fuel and provide optimum power.
Okay, Robin, on this airplane, the Cessna 152, is the propeller a fixed pitch or a variable speed propeller? What's the difference?
We're flying a fixed pitch propeller, which means the pitch of the prop is fixed by the manufacturer and can't be changed by the pilot. The propeller is mounted on a shaft, which is an extension of the engine crankshaft, so the prop RPM will be the same as the engine RPM. An airplane equipped with a constant speed prop has a governor which is continuously adjusting the propeller blade angle to maintain a constant engine speed. If engine RPM increases as a result of a decreased load, like in a descent, the system automatically increases prop blade angle, which increases air load until the RPM has returned to a preset value. This type of prop is more efficient in various flight conditions.
Okay, describe for me the type of ignition system on this airplane.
The ignition on this aircraft is provided by 2 engine-driven magnetos and 2 spark plugs per cylinder. The system is completely independent of the electrical system. The magnetos supply the current without any external source. To get them started, a battery is used to operate a starter, which cranks the engine.
All right, tell me about the fuel system on the Cessna 152.
It's a gravity feed system. Using gravity, the fuel flows from 2 wing tanks to a fuel shutoff valve, which if turned on, allows fuel to flow through a strainer and then to the carburetor. The fuel is then mixed with air and goes into the cylinders through intake manifold tubes. It holds up to 40 gallons of usable fuel with extended range fuel tanks.
And so why do we need to have fuel tank vents in this airplane?
Venting prevents a vacuum from forming in the system, which would prevent the flow of fuel by gravity.
And speaking of fuel, what kind of gasoline does this aircraft use?
The approved fuel grade is 100-octane low lead, which is colored blue. It is possible to use 100-octane fuel, which is colored green, but I wouldn't normally do so. If red fuel, which is 80-octane, were found in the tanks, that would be a no-go item.
Okay, Robin, how about the same question, this time for oil?
Multi-viscosity SAE 10W30 ashless dispersant oil. It holds 6 quarts, and I should never let it go below 4 quarts.
Okay, how about describing the electrical system in this airplane?
It's a DC system that runs off an engine-driven alternator that provides 60 amps of current. It uses a 24-volt battery, but the alternator actually provides 28 volts because there is extra energy needed to keep the battery charged.
And how about the ammeter? What does it indicate to you?
It basically indicates the flow of current in amps from the alternator to the battery or from the battery to the electrical system. If my alternator goes offline and is no longer functioning, or the electrical load exceeds the output of the alternator, it would then show the discharge rate of the battery.
Okay, one more question. You're flying along and all of a sudden accidentally the master switch is turned off. Would that have an effect on the aircraft systems?
Well, turning off the master switch will turn off all the electrical equipment on board the aircraft, including the nav and comm radios, lights, etc. The engine will continue to run normally on the magnetos.
Okay, what can you do if you get too cold or warm in the aircraft?
There is a cabin air control, which essentially routes fresh air in through vents, and a cabin heat control, which routes outside air over the exhaust manifold that gets piped into the cabin. If we use heat, we need to watch the carbon monoxide button because there is a danger in that any exhaust leak will bring carbon monoxide into the cabin.
Okay, we kind of shifted gears here, and now we're inside the cockpit. So let's talk about some of the instruments. What are the instruments that use the pitot-static system?
The altimeter, vertical speed, and airspeed indicators. Only the airspeed indicator uses input from the pitot tube.
So explain to me how the altimeter works.
Inside this device, there are aneroid wafers that expand and contract as the atmospheric pressure changes, sort of like a balloon. Then through a shaft and gear linkage, pointers on the dial are rotated.
So if you change the altimeter setting, say, from 29.15, or let's say to 29.85, what change is going to occur?
The altimeter will indicate a higher altitude. Changing the altimeter setting by 1 inch of mercury equals about 1,000 feet of altitude change. A higher altimeter setting gives you a higher altitude readout. A lower setting gives a lower readout.
Okay, how about the airspeed indicator? How does that work?
It compares the dynamic pressure of oncoming air hitting the pitot tube against the density of static air sensed at the static port. As the dynamic air input increases, it expands a little sealed capsule inside the instrument, which then drives a pointer on the face of the gauge.
All right, tell me about the various colors you see on the airspeed indicator and what they mean.
Well, let's see. The white arc represents the flap operating range. The lower airspeed limit of the white arc is VSO, or stall speed in the landing configuration. The upper airspeed limit of the white arc is for VFE, or maximum flap extension speed. The green arc indicates the normal operating range. At the low airspeed end of this green arc is VS, or stall speed clean. At the upper airspeed limit of the green arc is VNO, which is normal operation speed, or maximum structural cruise speed. The yellow arc indicates the caution range for operating in smooth air. The red line, or VNE, is the maximum speed for operations in smooth air.
Now, what instruments have gyros?
The turn coordinator, heading indicator, and attitude indicator. Usually the turn coordinator is electric, and the other two are vacuum-driven, although all three can be electrical.
Oh, very good. Now, while we're talking about the vacuum systems, how do they operate?
An engine-driven vacuum pump draws air through the instrument cases of the attitude indicator and the heading indicator, and then is vented outside. This air is directed at the gyro rotors to spin them up to their high speed. The output of the pump can be monitored on the suction gauge, which usually has a green arc of about 4.5 to 5.5 inches of mercury.
Okay. What can you tell me about compass errors?
Well, there are 5. Oscillation error, which is caused by turbulence. Deviation error, caused by electrical or magnetic disturbances in the aircraft. Variation error, which is due to the angular difference between true and magnetic north. I refer to the isogonic lines of variation for this. Acceleration error occurs on east or west headings while accelerating or decelerating. I use the memory jogger ANS, which stands for accelerate north, decelerate south. Northerly turning error, which occurs due to the compass leading in the south half of a turn and lagging in the north half of a turn. Another memory jogger here is UNOS, which stands for undershoot north, overshoot south.
Robin, let's talk a little bit about system problems and emergencies for a moment. What would you do if you ran into detonation?
Well, detonation occurs if the engine was overheating or running rough, or I found the fuel and air mixture was too lean. I'd reduce both the temperature and pressure of the fuel-air charge by reducing power, reducing the climb rate for better cooling, enriching the fuel-air mixture, or by opening cowl flaps if available. Also, I'd make sure the proper grade of fuel has been used.
Okay, I have a hypothetical question for you. During a run-up and before takeoff, you switch the magnetos from both to right setting and notice no drop in RPM. What's going on?
One of two things. Either the left P lead isn't grounding, or the engine has been running on the right magneto only, as the left magneto has totally failed.
Okay, I have one more question for you. What would you do about an ammeter indication that's showing a continuous discharge in flight?
Well, first I would turn off the electrical equipment, and then cycle the master switch, in case it was a nuisance trip, taking the alternator offline unnecessarily. If the discharge continued, then I would switch the alternator side of the master switch off and pull out the alternator field circuit breaker. Assuming it was daytime, I would leave off all the non-essential equipment and fly to the nearest field where repairs could be made. At nighttime, I wouldn't assume I had any more than about an hour of battery life.
Robin, you know your airplane very well.
Robin continues to shine. Notice how the examiner only touches on each of the systems and instruments. It's unlikely the examiner will grill you on every possible scenario. The best preparation for these questions is to become intimately familiar with your airplane's POH. It's likely the examiner will ask some of these questions during your pre-flight inspection, so he or she can see how you correlate the POH to the airplane on the tarmac.